Hello. Yes, I'm starting webinar. We approximately 30-second take to online. Okay.
Yes,
Okay. Best of luck. All the best.
thank you. All right. So I'll begin. Okay.
Hmm.
So welcome everyone. I am Shubham Keshri, and I am a PhD scholar at the Department of Management Sciences, IIT Kanpur, and you are here for the workshop, An Introduction to Metaheuristics. This is organized as a continuation to the large-scale optimization workshop, and it is hosted by Brij Disa Centre for Data Science and Artificial Intelligence, IIM Ahmedabad. Okay, so the content of this workshop is as follows. We will review some details of the workshop. What will we cover and how is the structure of what is the structure of this workshop? Then we'll briefly go through the introduction to optimization. I am assuming that all of you have a background of optimization, so I'll be very brief on the details of some problems, and we will see if you have any doubt. Then we will discuss about the differences, not differences exactly, but what are heuristics and meta-heuristics. Then we'll see one kind of heuristic, which is known as the greedy algorithms. And then we'll go move on to the concepts of meta-heuristics, which is first the representation of a solution, then how is the objective function handled, the constraints handling techniques, and then we'll move on to local search. So this is the idea. We will see if we'll be able to cover everything today. If not, then we will move this local search to tomorrow's class. In the next class, that is tomorrow, we will cover simulated annealing, Tabu search, and if time permits, we will go to variable neighborhood descent. And on the third day, we will cover the basics of population-based meta-heuristics. Then we'll cover genetic algorithm, and again, if time permits, we'll go to ant colony optimization. Okay. And if you have any doubt, you can write in the chat, or if you have the option of unmuting yourself, you can unmute and speak to me. Okay. So all the details of this workshop will be available at this link, and the reference book which I have used for this workshop is this book. It is actually here, Metaheuristics from Design to Implementation. This is a very good book, and most of the things I'll cover in this workshop has been taken directly or indirectly from this book. Okay, I will try to provide the recordings of this lecture as well in this website as soon as I get hold of the recording. So yeah, I have talked about me. This is my website. You can look if you have anything to go through, and this is my email ID. All right. So what is optimization? Optimization refers to the process of finding the best solution from a set of feasible solution. The process of finding the best solution. Okay. So this is an important terminology right now. The best solution from a set of feasible alternatives or solution based on a criteria. More formally, it involves identifying a feasible solution that maximizes or minimizes an objective function. So you have a problem, and in that problem you have an objective to either maximize or minimize. You are trying to find that feasible solution. Why feasible? Because that problem may have constraints. You're trying to find a solution that satisfies that constraints and maximize or minimize whatever your criteria is, the objective function, respecting all the constraints. In essence, we are seeking the most effective solution achievable under problem conditions. So at times we don't have enough computational resources or don't have enough solution time to solve the problem. We are good enough we are okay with good enough solution. So in such cases, we will not find the best solution. We are good enough with the near best solution. So this is what we will talk about, how to find a near best solution to a given problem. So metaheuristic deals with such kind of solution methods where we don't know exactly what is the quality of the solution, but it is generally a good solution. Okay. Structure of an optimization problem. An optimization problem deals with two spaces. First is a search space and the other is the objective space. So an optimization problem can be formally written as a pair S, F where S is the set of all possible solutions, which is also known as the search space, and F is a function which defines the objective function. And any global optima, which is at S star, which belongs to capital S, at that point, the objective function is least among all the points. It is not least, it is less than equals to the objective function value at any other point in the search space. This is defined for a maximization problem. Applications, I guess you all are familiar with the applications of optimization. I have listed down very few applications like resource allocation, decision making, machine learning, and many more applications: logistics, finance, um, construction, transportation, everything. Most of the there are many applications to optimization problems. Okay, so we will see a little bit more on the spaces, the objective space and the search space, because we will require this idea when we are constructing representation of solutions for metaheuristics. You will get to know what is a representation of a solution, but for the time being, I just told you that we need these spaces because we will dive deep into how these spaces, how can we look into these spaces. So what is a search space? The search space is all possible solutions for an optimization problem. Actually, it should be feasible solutions. All possible feasible solutions to an optimization problem. An objective space, the space defined by the value of the objective function for all possible feasible solutions. It should be feasible solution. Every point in the objective space corresponds to a evaluation of a point in the search space. So suppose we have a two-dimensional search space, and any point in this space can be written down into two using two scalars x1 comma x2. So a vector of two dimension. And when we evaluate this using the objective function f, so suppose s is equals to x1 comma x2, and we obtain f of s, this will be the objective function. So suppose for solution A, this is the objective function f of A, and for solution B, this is the objective function f of B. So over here, our objective space is linear, one-dimensional objective space. A solution can have a higher value of objective function or a lower value of objective function. So the definition I have given here for an optimization problem considers that our objective function is one-dimensional, but we can have higher dimension for the objective function as well. I have given one representation of a two-dimensional objective function, but there can be m-dimensional objective function. Okay, and the techniques to handle this kind of objective of higher dimensions, the dimensions of more than one, is little bit different. In this course or in this workshop, we will only look into problems which has one-dimensional objective space. We will not look into problems which have more than one dimension in the objective space. But just for completeness, I have given an illustration of an objective space in two dimension. So over here, the solution space is of two dimension. Any point in this solution space will have two scalars x1 comma x2, and that will, when projected in the objective space, will correspond to one point. It will also have two values f1 comma f2. Okay, I have not written it correctly. I have written it f of b, but it should be f1 comma f2. F1 is the first objective and f2 is the second objective. Okay, so it is a two-dimensional objective space. All right, so there can be many methods to solve an optimization problem. Over here, you see that we have talked about, we have a set of feasible solutions. So if we know what are the solutions in the set, we can just pick one by one those solutions and obtain the best solution. So that is what brute force method is. It is a method of finding the optimal solution by enumerating all the feasible solutions of that problem. Okay. So in brute force method, it is an exhaustive approach. That means we will exhaust all the feasible solution in the search space that evaluates all the solution to find the optimal one. And this is an exact method. What is an exact method? It is guaranteed to find an optimal solution if given sufficient time to complete. So if this method terminates without any time criteria, then it is bound to give an optimal solution. Okay, so it is an exhaustive search. How does brute force method works? It enumerates all possible solutions in the search space. And when I am talking about search space, it is about feasible solutions for the problem. So search space is defined for the feasible solutions. Okay. Okay. And it evaluates for each solution the objective function of that respective solution. And among those, it selects the best solution based on the objective function, whether it is a maximization problem or it is a minimization problem. Okay, so we will just illustrate this using one popular example. It is a traveling salesman problem. I am very sure that you all are aware of this problem. Just for completeness and moving forward, we'll look into this problem. So what is a traveling salesman problem? It is a well-known optimization problem where a salesperson has to visit some cities and he has to visit each city exactly once and he has to return back to the starting city. So start from a given city, visit all the cities exactly once and then return back to the original city. The objective is to minimize the total distance covered. This can be done in many possible ways. So for this example, you can have, since all the nodes are connected to each other, A is connected to E, B, D, C, E is also connected to, so each node is connected to every other node. So there are 5 ways the traveling salesman can start. How 5? Any solution, you can write it as a permutation. So A, B, C, D, E and back to A. So it is not necessary to write A. Why? I'll tell you just in a minute. So it can go from A to B, B to C, C to D, D to E. And since it is a requirement to visit back the starting city, so you need not write A. So a solution can be written as A, B, C, D, E. And since all the cities are connected from one another, any city can take any position. So there are 5 feasible solutions to this problem. But this TSP suffers with scalability issue if you solve it using enumerative search or brute force method. So there are n minus 1 by 2 factorial. Sorry, so it is not 5 factorial, it will be 4 factorial because there is one starting city. The starting city is fixed. Since the starting city, so suppose the source city is A, so it should always start with A. So A cannot change, the position of A cannot change, so it will be not be 5 factorial, it will be 4 factorial. So A is fixed and the next 4 position can be taken by any other city. So it is n minus 1 by 2 factorial. And why by 2? So what is happening is any solution can have an image of itself. So those are duplicate copies of the same solution. That is why by 2. So why brute force is infeasible? So it shouldn't be unfeasible, infeasible. Because if the problem size increases, the computation time grows exponentially. There is a factorial. So the number of possible solution explodes. Exponential explosion is there. So if any solution is computed, the objective function of that solution is computed in a microsecond, a solution per microsecond. So for 10 cities, it will be 0.18 seconds. For 11 cities, it will be 1.81 seconds. For 12 cities, it will be just 19.96 seconds. But from 12 to 15, if you go, it will be 12 hours. And from 15 to 20, if you go, it will be around 1928 years. So yeah, so brute force method is not a feasible solution approach to solve TSP of all sizes. If you have a TSP of 10 cities, you can use brute force method. And it is the best possible solution method you can obtain for a 10 city problem. But if the city increases, this solution method, the brute force method, may not be feasible. Okay. Limitation of brute force method we have talked about. It is impractical for large problems and it is computationally very expensive. All right. So we'll see the classification of optimization problem. So optimization problem, optimization methods. Optimization methods can be broadly classified into exact methods or approximate methods. In exact methods, you can have various classifications. The classification which I am written here, it classifies into the ways of solving this problem. So first is branching. So for any problem, you can divide that problem into smaller parts. If you do that, then you are doing branching, and branching can be combined with other methods to solve that problem. Either you can do branch and bound, or you can do branch and cut, or you can do branch and price. By the way, branch and cut and branch and price are variants of branch and bound in a way. Okay. So, all right. Another method can be constraint programming. We will not talk about constraint programming. There are other methods as well, like dynamic programming, A star, and other methods as well in exact method. Approximate method have two classifications. First is a heuristic algorithm, and the other is approximation algorithm. So what are these two classifications? For approximation algorithms, you have a bound guarantee. So I have it here, I guess. Yes, for approximation algorithm, it offers a bound that the solution quality will be at most this worse. So if I have an epsilon approximation algorithm, it guarantees that the solution is within a factor of epsilon from the global minimum. So it will provide you a bound that the solution will not be worse than that. So if I'm writing two approximation algorithm, so it means if you have a solution, it will not be worse than twice as the value of the optimal solution. Okay, it is the worst case bound. So these are approximation algorithms. Heuristic algorithms doesn't provide you such bound. It can again be classified into two categories: problem specific heuristic and meta heuristics. In this session, we will go through one problem specific heuristic, that is the greedy algorithm for some problems like knapsack problem and TSP. Why are they known as problem specific heuristic? They are known as problem specific heuristic because they exploit the property of the problem to design clever methods to search for um, solutions, right? And meta heuristics, we will see what meta heuristics are. We will define meta heuristics and we'll see the classification. First is a single solution meta heuristic and the other is population based meta heuristic. We'll talk about it. Okay. So yeah, so I'll not go through these details, exact methods, what it does and all, and examples I have written over here. Approximate method, it aims to provide high quality solution within practical time. So for approximate method, for exact method, if the problem is actually difficult, it belongs to some class which is difficult to solve, then the time taken to solve that problem can grow exponentially. Approximate methods are workaround that it will say, okay, I will not be able to, I am not guaranteeing you the optimal solution, but this solution will be of high quality and you will be able to obtain it in comparatively less amount of time. You may not have to wait for years to get a solution. You can get it quickly. High quality solution quickly. The classifications, heuristic algorithms and approximation algorithms, we just talked about it. What is a heuristic? Heuristic comes from this Greek word. I'm sorry, I'll not be able to pronounce it correctly, so I'll not pronounce it at all. It means the art of discovering new strategies, rules to solve a problem. So those are so what are heuristics? Heuristics are clever strategies to solve a problem. Either it can be a standard strategies to solve a problem. In that case, it is known as a meta heuristic. So if you have a standard strategy set to solve any kind of problem, then it is known as a meta heuristic problem. But if your strategies are dependent on the problem properties, then it becomes a problem specific heuristic. Then it becomes a heuristic. Okay. So it focuses on obtaining good enough solutions quickly. So that is a key factor. The solution should be obtained relatively quickly as compared to exact methods. It lacks approximation guarantee. Like approximate method and exact method, you will not be able to get the optimality gap. How worse is the solution? But it gives good solution. Include problem specific property, and so this includes problem specific heuristics and meta heuristics. So under the classification of heuristics, you get both kinds of heuristics, problem specific heuristic and a meta heuristic. Any questions? So you can write in the chat if you have questions. Yes, the PPT will be shared. I have given a link. You can go through that link and obtain the PPT as well as the recording once it is available. Okay. What are problem specific heuristics? Problem specific heuristics, again, since it is a heuristic, it will provide you good enough solution, but it uses the domain knowledge or intuition, or you can say it exploits the problem property to define the algorithm for that problem. What are the advantages? It is simple and computationally efficient, effective for solving small and well-defined problems. It shouldn't be small. These PPTs are made for different course, so I have taken it from there. So there are some errors, and I have updated it today afternoon. So there are some errors. Please pardon me for that errors. Examples. So greedy algorithm is an example of problem-specific heuristic. We will see examples of greedy algorithm. Rule-based methods. So I can give you some rule-based methods. So suppose you have some tasks to do and you say um, uh, least processing time first rule. So you are saying whichever task has the least processing time, schedule that first. Do that task first. So these are rule-based methods. These are quick, easy to understand, and easy to implement. So suppose you have some task to do, some task like it can be any task. Those are coming from scheduling problems, and you have to process all the task, complete all the task, and a simple rule can be whichever task takes the least amount of time, do that task first. So this is a rule-based heuristic. Limitations of problem specific heuristic, not guaranteed to find global optima. And this is true for any kind of heuristic, not particularly for problem specific heuristic. It can perform poorly for complex and poorly understood problem. Complex and poorly understood problem. So when the problem is complex, it is difficult to come up with a problem specific heuristic. And therefore, if you use some problem specific heuristic for a very complex problem, it may not perform well. And poorly understood problem, so you have not understood the problem properly and you're not able to exploit the properties of the problem, and therefore you're not able to define better problem specific heuristics. Okay, so what are metaheuristics? Metaheuristic search methods are higher level general methodology. So problem specific heuristics are designed for a particular problem, but meta heuristics are a higher level general methodology. So it is a very well defined strategies that works for majority class of problems. So it is a higher level general methodology that can be used as guiding strategies in designing underlying heuristics to solve specific optimization problem. So slightly differently it is written. So what it is saying is meta heuristics are general rules which you can use to again define new heuristics for specific problems. So meta heuristics, you can utilize meta heuristics to make a heuristic out of that meta heuristic. All right, and these are general strategies. It can be employed to any problem, not any problem, diverse kind of problems. So general purpose framework for solving optimization problem. It is a high level problem independent strategy. This is very important. It is problem independent. It works for various kinds of problems, for exploring large search spaces. So this search space is talking about the set of all feasible solutions to find high quality solution. What is the key idea? So we will talk about exploration and exploitation. Just a minute. Okay, so I have a separate slide on exploration and exploitation. So I will skip for the time being, and when it comes, we will talk about it. Okay, and parameterized and adaptable for different problem representations. So when we talk about representation, you will see that any solution for a problem, you can represent it differently. So for example, the traveling salesman problem, which we had, it we are representing a solution with a permutation. So this is a representation of the traveling salesman problem. Depending upon the representation, you can use different kinds of meta heuristics. Okay, so you can your meta heuristics can be deterministic or it can be stochastic. So these are the things which are written here. It is not guaranteed to give global optimal solution. It may give you global optimal solution, but you will not have any guarantee that the solution is globally optimal. Okay, this is a very important slide. You shouldn't use meta heuristic for any problem. There should be reasons for you to use meta heuristics. Okay, so when to use meta heuristics? When the problem is very complex or large, or it is combinatorial problem and exact methods is too slow. So you shouldn't blindly use okay, I have a problem, I will use a meta heuristics. There should be specific reasons for you to use a meta heuristic. So these are the some of the reasons. The search space is massive. So you have a very large search space, and I'll give you one example. So the shortest path problem, it can be solved efficiently. So if you have a directed acyclic graph using dynamic programming, you can solve it in linear time. So V is the number of nodes and E is the number of edges. So if you have a shortest path problem on a directed acyclic graph, if you don't know these terminologies, it is not very important. I'm giving you the idea. So for a shortest path problem, for a directed acyclic graph, it can be solved efficiently. So from one node to the other, you can obtain the shortest path in order V plus E times. But if your graph is very large, so for example, navigation problems, if you want to go from one city to the other or from one point to the other, these graphs are very huge. Even though you can solve it in exactly and in linear time, the time taken to solve that problem will be large, and therefore you might be required to use some kind of heuristic or meta heuristic. Okay, so these are real time problems. So for real time problems you may require meta heuristics even though exact method exists. Okay, so there has to be specific reasons for you to use a meta heuristics. You just cannot use a meta heuristic because there may be exact algorithms that solve your problem in the required time. Every problem you can have has a time you can give to solve that problem. So if it suffices to use an exact method, you should always go for an exact method, because you'll have an optimality guarantee that this solution is so this much far from the optimal. Okay. All right. When to use exact methods? Efficient solution algorithm exist. Problem instances are small and can be solved to optimality. Um, Optimal certificates are required. So you are required to give what is the quality of your solution, how far is it from the optimal. So in that case, some way or the other you have to obtain a bound, and it is better to use exact method. It is not definitive that you have to use exact method, but these are preferred. Okay. All right. For LP, for linear programming, there exists polynomial time algorithm, and you shouldn't use meta heuristics for solving LP. Okay. By the way, simplex is not polynomial time. Simplex is actually not exponential time. Interior point method is polynomial time algorithm to solve LP. Summary: meta heuristics are most favorable for large hard optimization problems. I have loosely used the term hard, where exact approaches are too costly. Okay, now we'll look at greedy approaches. So what is a greedy algorithm? A greedy algorithm, also known as constructive algorithms, builds a solution step by step, making a locally optimal choice at each step without backtracking. So it constructs a solution. That is why it is known as constructive algorithm. So a solution for to be solved using greedy algorithm has to be thought of as a set of elements. So suppose you're talking about the traveling salesman problem. The traveling salesman problem has edges. So A to B, B to C, C to D. So these edges can be individual elements of a solution. Once you have a solution which covers all the nodes, that set of edges will give you a solution to the traveling salesman problem. So first, to define to implement not implement sorry to design a greedy algorithm for a problem, you have to identify what are the elements that constitutes a solution to a problem. So for a traveling salesman problem, we are seeing the elements can be edges. You can also think about that the elements are nodes. So what are the order in which you are visiting the nodes? So you can also think that we are picking nodes one at a time. Okay, so first is the you have to define the solution as a set of elements. So currently for a traveling salesman problem, we have defined it as a set of either edges you can say or nodes you can say. Okay. Then from an empty solution, you have an empty solution, the greedy algorithm will pick one by one. So for a traveling salesman problem, the source node is fixed. So suppose A is the source node. Now you have to have some heuristic to pick a next city. So what should be the next city? There should be a heuristic to tell you that. So at each step, it selects the next element that seems best according to your heuristic. So for a traveling salesman problem, a very popular heuristic is a nearest neighborhood algorithm. So what it will do, whatever city is it is at, it will see what is the nearest city. So suppose from city A, city C is the nearest. So we have picked the next city, and then the next city, and then the next city. So in this way, the solution is built. So the you will obtain a solution at the termination of this algorithm. So this is very important. When we go to meta heuristic, you will see the difference. Okay. So for a greedy algorithm, we are constructing the solution one at a time. We are constructing the solution one element at a time. And you obtain a solution only when the algorithm terminates. Okay. So continue until the complete solution is found. Okay. For a knapsack problem, you can also have a greedy heuristic. So I hope you know what is a knapsack problem. There is a knapsack which has a capacity of W, and you have some items, n number of items. Each has some weight wi and a value vi. What is the decision? You have to pick some items such that your capacity of the bag is not exceeded. So this W is not exceeded, and you want to maximize the value you are obtaining from the items you are picking. So the decisions are binary, whether you are picking that item or not. And the goal is to maximize the value without exceeding the capacity of the bag. Okay, I have written it mathematically. This is an integer programming problem. You can just look at it afterwards if you don't know about it. How can we design a greedy heuristic? First, we have to identify what elements will form a solution. So what will be a solution? A solution is a set of elements. So whether you are picking A, B, I will not write A, B because we have used it for TSP. I'll write small a, small b. So A, B, and D, or you have picked E, F, and K. So a set of elements are the set of objects you are picking. So any solution of a knapsack problem can be broken down into picking an object, and the set of objects you are giving becomes the solution to the problem. Okay. So what we will do is we will need to have a heuristic, greedy heuristic to pick an object. So what will be a greedy way to pick an object? Pick the object which has maximum utility to weight ratio. So whichever maximizes the utility and minimum with the minimum weight, that is my most lucrative item. Pick the item with the maximum utility to weight ratio. So that is what we are doing. We are finding the utility to weight ratio for each item. We see that item 3 had the highest utility. Let us pick that item. So when I pick that item, what I will do is I will see what is the capacity it is using. So for the solution to become, for this solution, the first element I have picked is element 3. So I will say E3. Now I'll see whether I can pick another item or not. So what is the weight of element 3? The weight of element 3 is 5, and my capacity of the bag is 15. So I can add more items. Let us see if we can add any other item. So we will see that, okay, we can next pick from 0.75, 0.6 and 0.65. This is the highest. Then we can pick element 2. And this way you can construct the whole solution. I have given the illustration. You can go through it and it is easily understood, I guess. Okay. The observation, the greedy approach is simple. So it is very simple. You just need to identify the element that constitutes a solution, and then you have to find a heuristic to pick the next element. Okay. And intuitive, and it provides a feasible solution, but it doesn't guarantee to produce an optimal solution. That is true for all a heuristic. Okay. Okay. We will skip this. Now I am saying that this heuristic may not be optimal. I have given you a counter example. So for example, I have a bag of capacity 4 and I have 3 items to pick from, A, B, and C. Those has a weight of 3, 2, and 2, and the value is given over here. You see, the capacity to the value to weight ratio, if you obtain, you will pick item A first because it is 0.6. Value to weight ratio is 0.6. If you pick item A, you will see that the weight of the item is 3 and your capacity is 4. Therefore, you are not able to pick any more item because the weight of item B is 2 and the weight of item C is 2. Therefore, you will give a solution of item A. This is as the solution from a greedy algorithm. But the optimal solution is B plus C. The optimal solution is B and C. Why? Because you see, the value you will obtain is 2, which is higher than 1.8, and it doesn't exceed the capacity. Okay. So this is just a counter example to show you that greedy algorithm need not give you uh, optimal solutions. Okay. We have talked about TSP for nearest neighbor. We will not go through it again. You just go through it and you will see how it works. What is the template of greedy algorithm? First, initialize a solution as an empty set. Then select the next element using a local heuristic. You should have a local heuristic to pick the next element. Check for feasibility if that adding that element to the solution makes the solution feasible or not. Check that feasibility. If it is feasible, then add it to the solution and repeat. Okay. So start with an empty solution, pick one element using a local heuristic, add it to the solution, see if that solution is feasible or not. If yes, then add it to the solution, otherwise discard that element. Okay. This is a template for greedy algorithm. Okay. So we have talked about the design elements of greedy algorithm. You have to have a idea of what are the elements of the solution. You have to have a heuristic to pick the element, and then you can define the algorithm. Okay. Okay. All right. Why to use a greedy algorithm? Because these are simple, fast, and easy to implement. These are effective and memory efficient. You don't need to have a lot of memory. Okay. However, their limited local view. Why it is local view? Because it is just looking next. It is not combining some elements and seeing what it is happening. It is taking one element and then looking next. It is very myopic in nature. It is just looking the next item. It suffers from inaccuracies. That is what it is saying. Okay, now we are moving on to the concepts of metaheuristic. Till now, we have just talked about from the broad classification, from the heuristic, we have talked about problem specific heuristic. Now we are coming to meta heuristic. I'll just show that classification. Okay, so we were here. For heuristic algorithm, we had two classification: problem specific heuristic and meta heuristics. We are done with problem specific heuristic. Now we'll talk about the concepts needed to understand meta heuristics. Then we'll move on to single solution heuristic. Okay. So now we are moving on to the concepts required to understand meta heuristics. Any questions? Am I going fast, slow? Any feedback? All right. So what is a representation of a solution? You see, why do we need a representation? That is the first question you should ask. In a greedy algorithm, when we saw that greedy algorithm, what it does is it is constructing the solution by breaking down into set of elements. So it picks an element and then constructs the solution. For metaheuristic, that is not the case. The metaheuristics works upon a solution. So you should have a solution. And the metaheuristic would try to mutate or try to change that solution in a way that its objective function improves. So the main idea of a metaheuristic is it should have a starting solution to work with. And then it will try to improve that solution somehow, some way or the other. In a hope that, not in a hope, it tries to improve that solution in a hope to reach the global optima, but it may not reach the global optima because nothing is guaranteed over here. Okay. That is why we need a representation of a solution, because you need to have a solution in hand and then you will try to manipulate that solution. Okay, we will know more about it when we see examples and we dive deeper into meta heuristics. Okay, so a solution representation, this is how a solution are encoded for optimization problem. So for the traveling salesman problem, we are saying that we will represent a solution as permutation a, b, c, d, e, f, g. This represents a solution for a traveling salesman problem. We are defining the representation of a traveling salesman problem as a permutation of nodes. So this is the representation we are using. You can define another representation. How can you define another representation for a traveling salesman problem? So suppose you have, how many cities I have written? 3, and 7 cities. So 1, 2, 3, 4, 5, 6, 7. So this is city A, this is city B, C, D, E. Let us work with 5. Okay. All right. And suppose you have a solution like B, E, D, C, A. Okay. So we are in the permutation representation, the traveling salesman problem for 5 cities is written like this for that solution B, E, D, C, A. This is the permutation representation. Now I am defining another kind of representation. This is actually known as discrete value representation. We will see. But how are we representing it? So what is the position of city A? City A is at a position of 5. City B is at a position of 1. City C is at a position of 4. City D is at a position of 3. And city E is at a position of 2. So this 5, 1, 4, 3, 2, this can also represent a solution to the traveling salesman problem. Why discrete valued representation? Because each value is a discrete number. Each value is a discrete number. That is why this is known as discrete value representation. So over here we have represented TSP using discrete values. The question is which one to use. we will see which is preferred for which, but these are different representation for the same problem, same solution. This will give you the same objective function as this, because basically they are the same solution. Visiting city B to city E to city D to city C to city A. This will also do the same thing. Okay. So uh, defining a representation of a problem is also very important. How should you represent your solution? Because whatever you do next depends upon the representation you are using. Binary representation. By the way, not all kinds of representation can be used for a problem. It is problem specific. So one kind of representation may be used for a problem and other is not suitable. So for binary representation, you can take an example of a knapsack problem. So suppose you have 6 elements, element 1, 2, 3, 4, 5, 6, A, B, C, D, E, F. There are 5 elements. You can have a binary representation. So if I say like this, so it means A is picked, C is picked, D is picked, and E is picked, F is picked. So this is a binary representation for um, a knapsack problem. Okay. Real valued representation. So for continuous problems, it is generally preferred to have a real valued representation. So for example, if you have a continuous value of velocity, so you can just represent it as continuous numbers. Discrete value representation, I just gave you one example. Permutation representation, we have just seen traveling salesman problem. It is also used in scheduling problems. So suppose you have 5 jobs, J1, J2, J3, J4, and J5. So this is a permutation representation, that is 1, 2, 3, 4, 5. So you process job 1, then process job 2, then process job 3, then process job 4, then process job 5. This is also a permutation representation. No number is repeated again. Okay, permutation representation. Okay, so there was a question in the chat. Just I'll sick. The initial solution must be feasible for the yes. So actually, it is not exactly yes. So what happens is some metaheuristics are designed in such a way that it can handle either feasible solution or infeasible solution. But in general, most of the metaheuristics which are popular, I'll not say popular, but in general, the solution need to be feasible. The initial solution needs to be feasible, but you can design a metaheuristics that can initiate even with an infeasible solution. Okay. So I hope I have answered your question. And others, if you have any question, you can just post it in the chat. I'll answer your questions. Okay, I'll not repeat again because I have a lot to cover. Binary representation, I have talked about an example of knapsack problem. Real valued representation. Linear programming is a good example of real valued representation. If you have variables which take real values, continuous values, we are using uh, real valued representation to represent. We can use real valued representation to represent that a solution to that problem. Discrete value representation. An assignment problem is a very good example of uh, discrete valued representation. So how? So suppose there are machines. So suppose there are two machines, machine 1 and machine 2. You can say machine 1 has some jobs. So you can say job 1, 2, and 3 is in machine 1 and 4, 5, and 6 are in machine 2. How will you represent this? So suppose there is a vector. This is a vector for machine 1, this is a vector for machine 1, and this is a vector for machine 2. And you are saying 1, 2, and 3 is in machine 1, 4, 5, and 6 is in machine 2. So these are assignments. You can think about not just assignment of jobs to machine, because there are sequence also coming. You can think about task to person. So there are suppose 5 persons and 5 tasks. So person 1, person 2, person 3, person 4, and person 5. You have 5 places. You can fill it. So suppose task 3 is assigned to person 1, task 4 is assigned to person 2, task 1 is to 3, task 5 is to 4, and task 2 to person 5. So these are discrete value representation for an assignment problem. Okay. Permutation representation, traveling salesman problem is a very good example. A scheduling problem is a very good example. Okay. Why representation is important? I guess there is a question. Which metaheuristic do you suggest for? When we see different kinds of, by the way, it is not very easy to tell you which metaheuristics you suggest for assignment problem. You need to have more idea about your problem, because there can be multiple constraints and handling different constraints require different considerations. So it is not very easy to just prescribe that use this for this problem and use this for that problem. Okay. It depends upon what you want, how quickly you want, and lot of considerations are there. You will learn as you go forward. Why is representation important? So any metaheuristic requires a way to encode a solution. Okay, so this term is technical term used in metaheuristic community known as encoding. So whatever we are talking about right now, that representation is known as the encoding of a solution. We are encoding a solution using that representation. So any metaheuristic requires a way to encode solutions. The choice of representation impacts the efficiency and effectiveness of a metaheuristic. This is very, very important. So for the traveling salesman problem, we saw two representation: permutation representation and discrete value representation. One of them works very well, but the other will have some discrepancies in effectiveness. Okay. We will see what we are talking about in later sections, but the representation impacts your efficiency and effectiveness. How well your metaheuristic will work depends upon how you are representing the solution and other things as well, but representation is important. Must be relevant to the optimization problem. This is not very important. Okay, key characteristics of a good representation: completeness. Any solution, any feasible solution must be not it can be represented using a representation. So for example, the traveling salesman problem where you are using permutations, any permutation, any solution can be represented as a permutation. That is known as completeness. You should define your representation in such a way that all possible solutions can be represented. Okay. Connexity. So this you will know when we will talk about neighborhoods. But what does it mean? That from one representation you should have a path that can take you to another solution. So for example, traveling salesman problem with city A with the solution A, B, C, D, E, there has to be a way to reach the permutation B, C, D, A, E. There has to be a way. These two solutions must be connected. So when I'm talking about connected, you will know when we talk about neighborhoods. Okay. So any solution should be reachable through the search. From one solution, you should have a path to the other solution. That is what connexity means. Efficiency, it should be easy to manipulate. Your representation shouldn't be hard to manipulate. By the way, we have talked about very few representations. There can be many, many more kinds of representations. We have just talked about a bunch, just a bunch. Okay. We have talked about that example of a traveling salesman problem. Okay. Okay. Now this becomes important. Let me, what should I do? Let me talk about this right now. So we talked about two kinds of representation for a traveling salesman problem: a permutation representation and a discrete value representation. So you see, let me write a solution for a traveling salesman problem using permutation representation for 5 cities. So suppose I have B, D, E, A, C. So this is one representation, which is a permutation representation. Another can be 1, 2, 3, 4, 5. Okay, so we can have discrete value representation. So B is in position 1, A is in position 4, C is in position 5, D is in position 2, and E is in position 3. This is also another representation of a solution for a traveling salesman problem. Now you see, whenever you manipulate, how do you manipulate a representation? You can swap two cities. You can swap two cities. You can either pick one city and bring it here. You can do some manipulation to that solution. Whenever you do a manipulation to a permutation representation, it will always be a feasible solution. You will not have any repeating city. You cannot, in a permutation representation, you cannot have a repeating city. You cannot have A, B, A, E, A, C. This is not a solution. This is not a correct permutation representation because A is repeated. But for a discrete value representation, if you try to manipulate, suppose you are mutating randomly. So one can take any value from 1 to 5. So suppose you mutated this solution 4, 5, 2, 3, and for 1 you mutated it to suppose 3 again. So you see, you are saying that B is also in position 3 and E is also in position 3. This is not possible. So a permutation representation ensures all cities are visited exactly once. Moreover, you are leaving out on one. So over here, you are not able to write a correct solution. So this permutation representation is better suited for a traveling salesman problem. Why? Because it takes care of the constraints that each city must be visited exactly once. This representation has the inaccuracy that it may give you two cities at the same position and you don't know what to do. Therefore, permutation representation is more suitable for traveling salesman problem. And the higher level idea which I am trying to convey is your representation matters a lot. It can help you reduce constraints in your problem. You can define clever representation such that you have to deal with less number of constraints in your less number of constraints in your problem. Okay. We will see one more example about this. There's a question in the chat which says, why do we can do avoid repetition in the other? Yes, what you have to do is, over there we had a, so suppose it was 1 2, so 4 2 3 1 5, suppose this was the representation, and you do mutation and you obtained 4 3 3 1 5. This is not a correct solution to the, there is not a solution to the traveling salesman problem, but you can do repair. So if you have this solution and you manipulated it to become this, there's a repair strategy that, okay, I have a representation which is not a solution to the problem, let me repair this. So suppose you repaired this to 43215. Now this becomes a solution to the problem, but you had to do extra effort, you had to take extra effort to repair the solution. Why would I do that when I have a better way to represent the same solution using permutation representation? So if I have a better way, why would I take the extra effort of first manipulating the solution and then doing repair? Okay. So good question. Okay. We will talk about this swap and mutation later. All right. Okay. This is a very popular example, 8 queens problem. Now, what is 8 queens problem? So if you have a chessboard and there are 8 cross 8, I'm not drawing 8 crosses, but yeah, there are 8 cross 8, 64 boxes in the chessboard. And the question is, place 8 queens on the 8 cross 8 chessboard so that none attack each other. This is the problem. The problem is you have to place 8 queens such that none attack each other. So you can think about an assignment representation for this problem. So you have a 8 cross 8 board and you can say I have queen 1, queen 2, and you can just say in these 64 boxes, which position will have a queen. So suppose I'll say queen 1 is over here, queen 2 is over here. So this is an assignment representation. You're saying 64 boxes, where should a queen be? This is an assignment representation. Okay. But we can do better. I'll show you how we can do better. But first of all, you see there are 64 to the power 8 possibilities. The first queen can be in any of the 64 positions. The second queen can also be in any of the 64 minus 1, any of the 64 positions. So it is 64 to the power 8 possible um, representation to this solution. And there are constraints. So if you have this representation, you have to handle the constraints that two queens shouldn't attack each other. So that constraint you have to handle other way. Whatever you do, you have to handle that. You have a representation, then you have to check whether the constraints are being handled correctly or not. All right, is it clear? Right, the assignment representation has this issue over here right now, that if you represent a solution using assignment representation, you have to deal with the constraints. What are the constraints? That two queen cannot be in the same row, two queen cannot be in on the same column, two queen cannot be on the diagonal. These are the constraints you have to check after you have a solution. So you have a may have a feasible or infeasible solution. You have to check whether the solution is feasible or infeasible. We can do better. How we can do better? We can restrict that. Okay, since each row can have one queen, since each row can have one queen, I can just say one queen in this row. So each queen will have 8 positions to fill. So I will say queen 1 in any of these 8 position, queen 2 in any of these 8 position, queen 3 in any of these 8 position. So each queen has only 8 positions to fill. So we are reducing the search space from 64 to the power 8 to 8 to the power 8. Now we can again reduce this by realizing that each queen can only be in one column. So there are only 8 positions. So a queen can either be in this row and one column. So in this row, so I'll just draw it again. In this row, it can only take one position either here or here or here. Any one. The second queen can take any one position. So we can cleverly think about it, and you can notice that it is not 64 possible positions for each queen. It is just for each queen I can just think about one position in that row. The second queen one position in that row. So if we restrict all, if we restrict one queen per column, the solution becomes a permutation of 8 rows. So row 1, what is the number? So it will be like this. I'll give you the idea. So I have 8 positions, 1, 2, 3, 4, 5, 6, 7, and 8. So over here, what is that position? Over here, what is that position? Over here, and each has to be separate from one another. Otherwise, there will be conflict. If the first queen is in row 1 and the second queen is also in row 1, there are conflict. So it both cannot be in row 1. So if first queen is in row 1 column 1, if first, sorry, it will be row 1 column 1, the second queen, so if you think about that row, it will be row 2 and any of the 7 remaining columns. It can be 2, 3, 4 till 7. For the third one, it will be third row, but any of the remaining 6 position. So you just need one permutation to represent this solution. So you see, using the representation, you are getting rid of the constraints as well as reducing your search space. Force that one queen per row and column. It greatly reduces the search space and provides a natural encoding for the metaheuristic problem. So this is one example solution to this problem. There can be other examples as well. Is it clear? Okay, right. So this is important. Till now, there's a question. Okay, no. So till now, we have seen encoding. We have the representation. That representation is an encoding of the solution. That encoding has a decoding. That is known as, so the encoding is known as genotype. So these are taken from biology, and the decoding is known as phenotype. So the encoding and decoding, I'll tell you what these are. For a traveling salesman problem, the encoding and decoding are the same. So if I have A, B, C, D, E, this is the representation of a traveling salesman problem. The solution is exactly the same, A, B, C, D, E. This will give me a solution which will eventually be used to get an objective function. So if you have this, so what it means is, if you have this representation, you need no additional information to obtain the objective function value. I will repeat again. It means that if you have this representation for a traveling salesman problem, you need no additional information to obtain the objective function value of that problem. But for example, if you have a scheduling problem and if you have 5 jobs, A, B, C, D, E, you have the sequence. A has to be done first, then B, then C, then D, then E. But you don't know the time. What is the start time of A, the start time of B, the start time of C, the start time of D, and the start time of E. So this is the encoding. But to obtain the objective function value of that scheduling problem, you need to know the exact start time. So start time of A, start time of B, start time of C, start time of D, start time of E. Once you obtain the start time, then you will be able to obtain the objective function value for that problem. So this is the encoding, this is the decoding or that solution for the problem. This will not give you the required objective function because you need more information. But see it like this. If you, uh, instead of a permutation, if you write this scheduling problem as start times SA, so I'll have 5 positions, 1, 2, 3, 4, 5. So the first position is start time of A, the second position is start time of B, start time of C, start time of D, and start time of E. Then you will have it is known as real valued representation. This will be a value, 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 and this will be a value. This will give you the exact value of the objective function. So this the encoding and decoding for this representation is the same. Okay, is it clear? Encoding and decoding. Okay, all right. So type of mapping, so this is known as mapping, one-to-one mapping. So one encoding has exactly one solution. So it means one encoding will be mapped to exactly one solution. There will not be multiple solutions. So for example, this scheduling problem, you can have multiple solutions. The start time of A, B, C, D, and E, if you vary, this encoding can map to many solutions. So this is one-to-many mapping. You have one encoding, but multiple decoding. Similarly, one-to-one mapping, one encoding will have exactly one decoding, one solution. Decoded version is known as the solution. So for example, a knapsack problem. If you have the encoding, the solution will be unique. You will not have multiple solutions for the same encoding. By the way, knapsack problem represented as binary. You can represent knapsack problem differently also. In that case, it can be one-to-many mapping or many-to-one mapping. Knapsack problem, when represented using binary encoding, then it has a one-to-one mapping. One-to-many mapping, I showed you one-to-many mapping. Okay, so you have one, okay, scheduling problem I showed you. Here is one more example. So if you have AA, BB, so this is a partitioning problem. If you have a representation as AA and BB, and you have, okay, it is one-to-many, just a minute, many-to-one. All right, so let me just check quickly, one-to-many and many-to-one. Okay, so the one-to-many is, the first is the solution, and this is the representation. This is the representation. So it means one solution has one encoding. So this is one-to-one encoding. Every solution has one representation. One-to-many encoding. So if you have a partitioning problem where you're trying to partition some elements in 2 sets or 3 sets or n sets. So suppose you have two set A, not A, I'll not write A, some nodes. Suppose you have some nodes V1, V2, V3, and V4. So you have a graph with 4 nodes. You want to partition these nodes into 2 sets. So you can have V1, V2 and V3, V4. Okay, so this is one partition. The first 2 elements are in the first set and the second 2 elements are in the second set. So you can represent this solution. You can represent this solution using AABB. This solution to one encoding. You can have another encoding for this solution, BBAA. So A is a category and B is a category. So it just says the first 2 elements are in category A, the second 2 elements are in category B. The other encoding is BBAA. The first 2 elements are in category B, the second 2 elements are in category B. So one solution but many encodings. This is very inefficient. Your search space will have this kind of encoding as well as this kind of encoding, but your solution is the same. You're unnecessarily wasting time in different kinds of different solutions which have this different representation which have the same solution. Okay, so one-to-many mapping. Another is many to one mapping. You have many solutions, but all those can be represented as one encoding. So I gave you the problem of scheduling problem. So if you have one solution, you can have many solutions. The start times of A can be anything, the start time of B can be anything, the start time of C, D, and E can be anything, but all can be represented as A, B, C, D, and E if it follows this relation. S of A is less than equals to S of B, which is less than equals to S of C, which is less than equals to S of D, which is less than equals to S of E. For this relation, if you have a solution that can be encoded, but multiple solutions can be encoded to the same encoding. So that is many to one encoding. Many solutions, one encoding. Okay. All right, just give me a minute. All right. So I hope you have understood encoding and decoding. Now we'll talk about direct encoding and indirect encoding. So for one-to-one mapping, you have a direct encoding. You don't need to do anything. You just have a solution. You just have their representation. Nothing. There is no computational effort to converting an encoding to a solution. But indirect encoding, you have to have a heuristic or an algorithm that converts your solution to a representation and your representation to a solution. That is known as an indirect encoding. Okay, that is what I am saying. So you should have a decoder. So for example, in this scheduling problem, if you have this permutation job 3, then job 1, then job 4, then job 2, your metaheuristic will have this representation. But to get a solution, you have to have a decoder which will decode this representation to a solution. So you need to have a decoder which generates a solution. All right. So for this scheduling problem, you can represent it as a permutation, but there has to be some kind of heuristic which will tell you what is the start time of each of the jobs. You can say just um, earliest release date first, whichever is released first, you take that and you will obtain the start time of each of the jobs. Something like that. You get the idea, right? You have to have an algorithm which will tell you what is the solution for that representation. Now, earlier we have seen four kinds of representation. First was permutation representation, binary representation, then we saw discrete value representation. We saw some kinds of representation, but those representation, most of them were direct encoding. You can have indirect encoding, but this is a very good example of indirect encoding, random key encoding. What does it do? So suppose you have a permutation of jobs. So suppose four jobs are there. Instead of writing it as a permutation, so for example, the permutation is um, B, A, C, D, E. This is the permutation. What we will do is for each job. So let me define it indirectly. Suppose I have five jobs, which is A, B, C, D, and E. So for each job, I will give a random number. So suppose the first job is 0.6, the random number assigned to first job is 0.6, then 0.5, then 0.3, then 0.7, and then 0.9. So this is my encoding. What is my encoding? 0.6, 0.5, 0.3, 0.7, 0.9. This is my solution. Okay. How will we get the solution? This is my encoding. How will we get the solution? You arrange it in ascending order. So this is my decoder. So I have a representation 0.6, 0.5, 0.3, 0.7, and 0.9. I have a encoding. What will be my solution? You arrange it in a uh, increasing order, ascending order. So what is the least? This is the least. What is the position? C is in that position. Then B is in this 0.5, then 0.6 will come A, then D will come, then E will come. So you see, this is my decoder. So this is another form of representation, random key encoding. So this is another form of representation. We saw some form of representation, right? I'll just show you again for clarity. We saw these kinds of representation: binary representation, real valued representation, discrete value representation, permutation representation. This is another kind of representation, random key encoding representation. Why I am talking about this? Because it is easy to manipulate. You have real values. It is easy to manipulate. You can just say, I will, for each element, I will have a random perturbation. So zero point 0.6 can become 0.67, zero point 0.5 can become 0.57, something like that. It is easy to manipulate. That's why this kind of encoding. So your representation governs your manipulation strategies. It governs the efficiency of your solution approach. It is very, very important. That is the idea. Whole idea over here is your representation is very important. Any questions? Any questions? Okay. Are you guys here? All right. I hope I'm not boring. All right. Okay, you can call me just Shubham. Don't no need to call me sir. Okay. Okay, so next is I have written objective function, but it is actually the guiding objective function. Guiding objective function. Why? Because this will guide the search. Your objective function of the problem need not be same as the guiding objective function for the metaheuristic. So what is the definition of objective function? It just assigns a real value. If you have a one-dimensional objective function, it assigns a real value to each solution of the search space, and it tells you the quality of the solution. This is a technical term, fitness, which is used in metaheuristic community. It just means how good is your solution. The objective function value is known as the fitness. It can be the other way, so I'll explain you a little bit better. So fitness is, so for a minimization problem, lower is better. For a minimization problem, lower is better. Fitness is defined as the higher is better. So if you have a minimization problem, just take a negative of that. The higher the fitness, the better is my solution. That is all it is. For a maximization problem, the positive values, the higher the fitness, the better is my solution. That's it. Okay. The role of the objective function, role of optimization. Okay, it should be objective function. Okay. So it says guides the search towards a better solution. That objective function should guide the search towards a better solution. Poorly designed objective function can lead to ineffective optimization. If you have not defined your objective function properly, you may get stuck in local optimal. We will see what it is. Okay, so you can have self-sufficient objective function and a guiding objective function. What is a self-sufficient objective function? For example, traveling salesman problem. The objective function for traveling salesman problem is the minimum tour length, and that is sufficient for a metaheuristic. You can use that and your metaheuristic will work good. It will not have any issue. But there are some problems where your problem's objective function is not sufficient. You have to augment it. You have to change it such that the metaheuristics works in a better way. I'll give you an example to better understand this idea. You have to transform the original objective function such that it guides the search in a better way. A well-designed objective function ensures effective search, convergence to optimality or near optimal solutions. Yeah, the example is traveling salesman problem. It is self-sufficient. You don't need to add anything. The objective function of the problem is the distance of the tour, the total distance of the tour, and you can use that for the meta heuristic. For exam scheduling problem. So for example, there is a problem. What is the problem? A university must schedule final exams with no exam conflict. So if you define an objective function, so what is my solution? A schedule S is my solution. The objective of the problem is that there should be no conflict. So I can define an objective function saying it takes value 0 if the schedule has no conflict. Okay, minimum the better. And one otherwise. So I want if the solution has no conflict, the objective function takes value 0. And if the schedule has conflicts, the objective function is 1. I will repeat again. A university is scheduling some final exams, and the objective function it has defined is if my schedule has no conflict, my objective function is 0. That is the best solution I want. That is the solution I want. If my solution has conflict means our students have an exam at the same time slots two different exams. That is what a conflict means. So if my schedule has conflict, my objective function will take value 1, and I don't want those solutions. If you use a local search or any metaheuristic on this objective function, it is not a very good objective function. You will either have 0 or 1. So when you have 1, you have no idea where to go. I have a schedule S, some representation is there for the schedule. The objective function of that schedule is 1. You manipulate that schedule, you again get 1. You again manipulate that schedule, you again get 1. You don't know what to do, where to go. So this is not a very good objective function. A better objective function for this problem can be minimizing the number of conflicts. So you can define a variable which takes, it's a parameter which takes, no, it is a variable. It is dependent upon the variable. It depends upon the schedule. It is the number of conflicting exam pairs for student J. So what you will do is for each student, you will see whether he has a conflict or not, and you will count how many such conflicts are there. So for a given schedule, there will be some number of conflicts, say 10, and then you manipulate that and you see that the conflict increases. It went to 15. Then that 15 the schedule which gave objective function as 15 is not good. That conflict with 10 objective function is better than the solution which is having objective function of 15. Now you have a better way to guide the search. Your objective is to, you have an initial solution which gives you some value of the objective function, say 50 conflicts are there, and you are guiding that search, okay, take it towards 0. So you see, if a schedule 1 has a conflict of 50 and a schedule 2 has a conflict of 30, you know that at least this S2 is better than S1. But in the previous case, both the schedule gave an objective function of 1, infeasible. Both are infeasible. So you see here we have a better way to guide the search, move in this direction. Is it okay? All right. So I hope it is all right. Right. Now we have talked about representation. We have talked about objective function. This is very important, constraint handling, because in general, in an optimization problem, we have constraints, and your solution and your method needs to respect those constraints. You should know the ways to handle those constraints, and this is quite difficult to, not quite difficult, but this is relatively difficult to do as compared to the representation and the definition of objective function, because ensuring that your solutions respect those constraints and then guiding the search towards the local optima is a difficult task. Okay, so objective optimization problem have constraints, and this shouldn't be violated. Common strategies. What are the strategies to handle constraints? First is a reject strategy. This is very harsh strategy, by the way. What you do is you have a feasible solution. So for the example which we gave for traveling salesman problem, the discrete value representation. So I had series, so it was 4, 3, 3, 2, 1. So it says city E is in first position, city D is in second position, but B and C are in the third position, and A is in fourth position, and I don't have anything in the fifth position. This is not a feasible solution to the traveling salesman problem. So the reject strategy says that reject this solution. I don't want to include this kind of solutions. This, you can realize that this is a bad strategy. If your problem is a very constrained problem, your constraints are very tight, you will not be able to find any feasible solution. By the way, there are problems where the objective is to find a feasible solution. Just give me one feasible solution, I'm happy with that. So in such cases, you just cannot, you just doesn't have the liberty to reject solutions. Okay, so this is not a good strategy to do. Penalizing strategy. So what it does is, if you have objective functions and constraints, you can say, I will quantify the infeasibility. So suppose I have ax less than equals to b, where x is so this is not a vector. I'm writing a so I'll write an ax is less than equals to b. So this is one constraint, just one constraint. So what you will do is you will quantify the um, uh, penalty, or not penalty, infeasibility. What is the so how large is the infeasibility? So you will say b minus ax. If this is greater than 0, this is what my infeasibility is. This is how large. Okay, it is actually ax minus b. Ax minus b. How large is my violation? How much I am violating? So you take that violation and put it in the objective function with a penalty. That is what it is known as penalizing strategy. So what you are doing is you have an objective function. You have an objective function f of s for that problem. Suppose something you have, and you had a constraint which ax less than equals to b. What you do is you modify this objective function f dash of s and say f of s plus some alpha times ax minus b. Positive. What it means is just take the positive side, don't take the negative side. That is maximum. It actually means this as plus alpha times maximum of ax minus b comma 0. This is what it means. So you are modifying the objective function. You are changing the objective function such that the violation is being penalized in the objective function. So the more violated your solution is, the worse it becomes. For a minimization problem, by the way, this is all about a minimization problem. Your objective function will increase in value. If this becomes positive, that means your constraint is being violated. And since we are adding a positive number, this is also positive. Since we are adding a positive number to the objective function, the solution becomes less lucrative. It is a bad solution because the objective function is increasing due to the penalty. So it is in a way trying to avoid solutions with higher penalty, higher infeasibility. Is that all right? Repairing strategy. So we talked about repairing strategy. We were saying that we will have a solution and then we'll do repair some way. Some way we'll try to repair the solution. Decoding strategy. So you see, we can define the representation in such a way that the constraint is being handled. So that example of 8 queens problem, the representation is defined in such a way that it is handling most of the constraint. No two queens can be in the same row. No two queens can be in the same column. And then you can decode it. So this is decoding strategy. One is preserving strategy. It incorporates problem specific knowledge into the representation. Okay, so this is what it means. Sorry, the decoding strategy I'll come to. Preserving strategy is that 8 queens problem which I talked about. In the 8 queens problem, we are trying to make the representation in such a way that the problems constraints are being handled by the representation. So for example, in a traveling salesman problem, we are defining it as a permutation. Since it is a permutation, we are ensuring that no cities are repeated again. So that constraint of no city being repeated and no city being left out, all those are taken care by the permutation representation. Decoding strategy is something different. It says that when you are decoding a solution from an encoding, so you have an encoding, you are doing decoding, you handle that decoding in such a way you don't create a infeasible solution. So for example, that scheduling problem which we talked about. So we have a scheduling problem. So suppose that sequence is A, B, C, D, and E. You have a sequence of jobs. You decode it in such a way. You obtain the start time of A, start time of B, start time of C, start time of D, and start time of E in such a way that you do not violate a constraint. So the decoder handles the constraint. Okay. So reject strategy, it means that you just reject the solution. Penalizing strategy, the infeasibility is taken to the objective function and penalized. Repair strategy, you have obtained a solution, you try to repair it. Decoding strategy, the decoder ensures that the solution is feasible. It may or may not, but it tries to ensure that the solution is feasible. Preserving strategy, it says that build a representation in such a way most of the some of the constraints are being handled by the representation. So constraint handling is very important when you are trying to solve a problem using metaheuristics. Any questions? Okay, no questions. All right, either you guys are not able to understand anything or I don't know. Am I going too fast? All right, I just, okay, thank you. Right, so I've given you one example. I'm given you one example over here, one example of traveling salesman. No, sorry, it is a knapsack problem. So what it says is in knapsack problem, we have a binary encoding. So suppose I have four objects, object 1, object 2, object 3, object 4, and it is a binary encoding. Yes, you will get the recording, but I don't know I'll be able to give you immediately or not, but after the session, it will be available. I'll show you the link. When I complete, I'll show you the link where it will be available. And what was it? But will the recording be there? And if you have any questions, you can email me later. Okay, so for binary encoding for each object, you will just say whether you have picked that object or not. So suppose a solution with these two objects, object 2 and object 3, you have a feasible solution. Now suppose you manipulate this solution and you obtain another solution where all of them are 1, for example, and you see that this solution is not feasible to the problem. So I have given a repair strategy for a knapsack problem. It says that if a solution violates the capacity constraint, remove item iteratively. Now what you do is you try to remove one item and see whether the solution becomes feasible or not. So this is the idea of repair strategy for a knapsack problem. Okay, very simple strategy. But there should be clever removal of items. It is not random. You have to cleverly remove. I have given you what the idea, but the idea is just you have to cleverly remove items from the knapsack such that the capacity is again not violated. The capacity is respected. Okay. All right. So now we have completed the basic ideas of metaheuristics. I am running quite a bit late. I want to cover some portions today that I can then whatever is planned goes properly. Now we are moving to single solution metaheuristic. A very high level idea I'll give you over here. In any single solution metaheuristic, it works with just one solution because the name we have single solution, obviously it works with a single solution. It has a single solution. I'm giving you the higher level idea. It has a single solution, and from that solution, it creates a candidate of potential solutions. So constraint handling is meant to minimize the search space. Not necessarily. You see, your constraints are your problem constraints. Anyhow, you have to respect those constraints. Yeah, it is helping you in a way to reduce the search space, but that is not why we are doing it. We're doing it because you have to respect those constraints. So either you incorporate it in the representation or you handle it in some other way or the other. You have to handle the constraints, and handling constraints is difficult, by the way. If you have a very different kinds of constraints and you have to respect all kinds of constraints, you should have clever ideas of how to do that. Okay. All right. So, okay, high level idea of a single solution meta heuristic. We have a single solution. From that solution, we will create a candidate set. Okay, from this solution, this is the set. We will search the set, this candidate set, and we'll pick the next solution to work with. So suppose this solution is picked. Again, for this solution, I will create another candidate set. And I will see which candidate to pick. And by the way, we are picking the solution with a better objective function value. By better, I mean lower for minimization and higher for maximization. Okay. Again, for this solution, I will create another candidate set and I will pick one solution. So this is the idea of S meta heuristic. I have one solution. I will create a candidate set. I will pick the solution. And then again, I will create its candidate set and then pick a solution. Okay. And whenever I'm working with this solution, so this solution is known as current solution. So whosoever candidate set I am building, that solution is known as candidate solution. Is it clear? Okay. So it has a generation phase. From the current solution, it generates a candidate solution. We will see how are we generating the candidate solution, and we will not go through it any further. Replacement phase. Once we have a candidate solution, then we move on to the next candidate solution. We replace that solution. So it has two phases: generation phase and a replacement phase. Now you see, when we are doing generation phase, we can either utilize some memory from the past, or we may not use some memory from the past. So for example, if I was here, this was my candidate solution, and this was my current solution, and I build a candidate set, and I moved to a new solution. Then I build another candidate set. While building this candidate set, did I use information from the previous set or not? If I'm using previous information, then we are using search history. Tabu search is one example. If I'm memoryless, I'm not bothering about what was the candidate set before, then it is memoryless. Local search, simple local search is just one example of that. Okay. How are we generating new candidate set? We are doing local transformation, that is known as neighborhoods. We will see what a neighborhood is. So this is the higher level idea of single solution metaheuristic. Clear? This is the template. Start with a solution, generate the candidate set, select the next solution, and repeat. And do this until the termination criteria is met. Local search, simulated annealing, tabu search are examples of single solution metaheuristics. Key takeaway: single solution metaheuristics are simple, effective, and efficient for many optimization problem, but require strategy to avoid getting stuck in local optima. Since we are working with single solution, and at each step we are moving to a solution which is better than the previous one. For simple local search, I'm not talking about tabu search or simultaneous. We move to a solution which is better. So what happens is you might get stuck in a local optima. You have to have strategies to avoid local optima. Simulated annealing, tabu search are algorithms which tries to avoid local optima. Local search, the simple form of local search, doesn't have any strategy to avoid local optima. It can get stuck in local optima. But simulated annealing, tabu search are built on the idea that, okay, suppose the solution which I have obtained from local search is a local optima. How can I avoid this local optima? So that is where these algorithms, the idea of this algorithm began. Okay. Neighborhood in metaheuristics. This is very, very important. That candidate solution which I was talking about is actually the neighborhood of that solution. What do I mean by neighborhood? I will not go into this much details. You have a solution, you will manipulate this solution, and that manipulation should be small. So for example, if you have a permutation representation for a traveling salesman problem, A, B, C, D, E, and F, one manipulation can be shift a node from one position to the other. So shift F from this to this position, shift E from this to this position. Okay. So this is a manipulation to a solution. So this kind of manipulations create neighbors. And all the possible neighbors you can obtain from one kind of manipulation. So suppose for a traveling salesman problem, we define the manipulation as swap moves. We will do swap. So the swap means we will pick two city, this city and this city, and we will swap its position. So this is swap move. So all the possible solutions you can obtain by all possible swaps. So you have this solution, do all possible swaps you can. Pick any two city and do the swap. Pick any two city and do the swap. All possible solutions which you can obtain from this solution using swap moves will become the neighborhood of this solution, will become the neighbors of this solution. Okay, is it clear? All right. What are move operators? Small modifications applied to the solution S that generates a neighbor. Small modifications. I'm not talking about do swap 7 times, do swap 10 times consecutively. You have to do one swap to obtain its neighbor. Okay, so you have a solution. So I'll just You have a solution, you do the swap, you obtain S dash. You do another swap, you have S double dash. You have S triple dash. One swap. All the set of those solutions will become your neighbors to S. Okay. Small modifications. Strong locality. So this is very important. What it means is small change in encoding should result in small change in decoding. Then it becomes strong locality. Small change in encoding should be small change in decoding, मतलब small change in the solution. So for example, if you have a knapsack problem and if you have 0, 1, 1, 1, so this is one solution. S is this. What you can do for generating a neighborhood of a knapsack problem, flip a bit. So you just flip this bit to 0. So this is a small change in the representation. How will the solution change? The solution was item 2, item 2, item 3, and item 5. This was the solution. When you flip this bit 1 to 0, you are just removing one item. You're just removing one item. Small change in representation, small change in the solution. This is known as strong locality. You can have weak locality. How is that? So suppose you have a problem of discrete value problem. So if your values can be take discrete values or integer values, for example. So it can take values from 1 to till suppose 70. So if you have an integer programming problem which takes value 1, 2, 3, 4, that variable takes value 1 to 70. And now what you are suggesting is for each solution, let me make it binary. So for 1 it will be 1, for 2 it will be 1 0, for 3 it will be 1 1, and so on and so forth. You are turning each integer to binary. Okay, so this is your encoding for this integer programming problem. Each variable will be its binary, it will be represented with its binary representation. For this problem and for this representation, this is weak locality problem. Why? Because you see 15 is represented as 1 1 1. So 15 is represented as 1 1 1 and 1, 4 ones. And if you do, suppose you do a bit flip, your operator is, so this is your solution, and you want to create its neighbor, and your neighborhood move operator is, and your neighborhood operator is bit flip. So what are you doing? I think I have talked a lot. Just bear with me. I have a solution. What I'm doing is I'm trying to create its neighbor. That is the idea, right? For single solution metaheuristic, I have a solution. I'll create its neighbor. So over here, I have a solution 15, which is represented as 1 1 1 1. And my method of creating a neighbor is bit flip. So suppose I flipped this bit and I have a neighbor 0 1 1 1. This is a neighbor of 1 1 1 1. Now you see, in representation form, in encoding form, this is actually its neighbor. I have just done one bit flip, but in the solution form, it has changed from 15 to 17. The difference is large, right? Small change in the encoding doesn't reflect small change in the decoding, the solution. So this is weak locality. Your neighborhood operator should be such that your neighborhood operator such and the representation both together should be such that it should have strong locality. Small change in the encoding should reflect small change in the decoding. Is it clear? Is it clear? Quickly. Okay. Traveling salesman problem, swapping two cities is a I have talked about. Another is reversing a subsequence of cities. This is known as 2-opt, very popular move operator in traveling salesman problem, and it is very why it is popular, because it works very well. There are actually k-opt operations also, but we'll talk about 2-opt. What is 2-opt? So suppose I have a permutation of cities like A, B, D, C, E, F, X, Y, Z. This is one representation. What does 2-opt do is it picks two cities and it will reverse the order. A, B, F, E, C, D, X, Y, Z. This is what 2-opt does. Okay. It reverses the order of the cities in between. This is 2-opt. So this is a operator, neighborhood generation operator. And this has strong locality in TSP. But same operator for scheduling problem has weak locality. Now you may question why. You see, these are details, but it will take time, but I want you to know these details. You see, I have the same representation, same operator, 2opt. What does 2opt do? Picks two cities and reverses the order. Same operator, same representation for TSP has strong locality. Same representation, same operator for scheduling problem has weak locality. Why? You see, for scheduling problems, the relative positions of the job. So suppose A, B, C, D, E, F, G, H. The relative positions of the job is very important. What does it mean? It means A and D has two jobs in between. D and F has two jobs in between. C and H has four jobs in between. The relative positions in scheduling is important. Why? Because that governs the completion time of the jobs. So completion time of A, completion time of B, completion time of C, and so on, completion time of H. If you change this, reverse this, for a scheduling problem, you see, although CH remains the same, CA remains the same, CB remains the same, CC remains the same. The completion time of all these jobs, G, F, E, D, all will change. So just one operator changes completion time of four jobs. That is not what we want. Small change in representation, small change in the representation should result in small change in the solution, but this will change a lot. But this is not true for traveling salesman problem. For traveling salesman problem, adjacency is the key. It is not relative ordering. A is adjacent to B, B is adjacent to C, C, D. So this adjacency is important. If you if you do 2opt, suppose I am doing 2opt over here. So G, F, E, D, C, and H. Now you observe with this 2opt, I have only changed two edges, this edge and this edge. Otherwise, all the edges are same. This edge is same, this edge is same, this edge is same, this edge is same, this edge is same. Other edges are same. So 2opt, small change in the encoding is changing small change in the solution. Is it clear? So 2opt in scheduling problem is a weak locality, but 2opt in traveling salesman problem is strong locality. Clear? All right. I hope it is clear. I have no time left. Okay. For knapsack problem, we have talked about bit flips. You can just add one and remove one. Okay. Continuous variable optimization, you can just add small perturbation and you can just say, so for continuous optimization, you can just say if I am at X, the neighbors will be X plus delta and X minus delta. So this is my neighborhood. Okay. Yeah. It is important. A well-defined neighborhood structure is crucial for the success of your metaheuristic. If you use a 2opt operator for a scheduling problem, your metaheuristic will be quite inefficient. Okay. Examples of neighborhood operator: 2opt, 3opt. Okay, I should talk about this. For 2opt, so for 2opt, what it is doing is, I talked about 2opt, right? So it takes two positions and reverses the order. For 3opt, actually, an example of graph will be better. So suppose this is the graph and this was the path. This was the path. Okay. What will 3opt do? It will remove three edges. Suppose these three edges are removed. And then it will create neighbors. It will create neighbors. So one neighbor can be this. Oh, sorry. It's one neighbor can be this. This is one neighbor. So you are removing three edges and then putting it back. So this is 3opt. In 2opt also, 2opt can be viewed as this only. So if you have 2opt in this, you just remove this edge and this edge. What it will do is, it will connect this and connect this. This is what 2opt is doing, by the way. It is removing two edges. It is removing two edges and then putting it back in a different way. So this is 2 opt, this is 3 opt. Insertion operator. So insertion operator, what it does is, so if you have A, B, C, D, E, F, and G. So what it will do is it will pick one and insert it in some other position. So that will become A, B, C, G, D, E, and F. I don't know why is my not. Just a minute. Okay. So this is what insertion operator is. Exchange operator, we talked about swaps. So just take two and swap it in between. That is swap operator. Inversion operator, this 2 opt and inversion operator are exactly the same. 2 opt and inversion are the same. Binary representation will have bit flips, and yeah, k bit flips. You can just not flip one bit, you can flip k number of bits. Real valued representation, you can add some perturbation random number in each values, and that is neighborhood creation for real valued representation. And by the way, this is in no way exhaustive. You can have multiple kinds of neighborhood. These are some examples of neighborhood operators. Okay. Hello. I think, yeah. Okay. Search space. So why I am coming back to search space again? You see, till now we talked about search space. Yes, 2 opt is like inversion. Yes, 2 opt. You are yes. Thank you for this comment. I know basics is very important. When you, if you understand this, you will be able to understand many kinds of meta heuristics which are applied in the works papers. Okay. Questions here, are you not? No, you are okay. All right. So search space. We talked about search space and objective space. Why I am bringing it back over here is we will define search space little bit differently once we have the idea of neighborhoods. Okay. So how is the search space defined? We will define the search space as a directed graph. As a directed graph. We will have nodes and we will have edges. The nodes are set of all solutions. The nodes are set of all solutions. And E is the directed edge representing a move operator. So I'll just show you. Suppose this is my solution S and all possible solutions. So yeah, S1, this is S2, S3, S4, S5, this is S6, this is S7, and so on and so forth. This is S8. Just a minute. Okay. So these are, suppose these are my search space S9 and S10. And so all this set of solutions, suppose you have 10 solutions in your search space. How will the graph look? So from this solution, you can reach this solution, this solution, this solution, and this solution. So these are your neighborhood creation operators. So from this solution, you can reach this, and this. From this solution, you can reach this and this. From this solution, you can reach this, you can reach this, and you can reach this. So you see, in this way, you can create a graph. And this is how the search space from now will be defined. The search space will be represented as a directed graph where you have nodes and edges. The nodes are set of all possible solutions and the edges are set of directed edges representing move operators. There is an Si to Sj that belongs to the set E if the solution Sj can be generated from Si through a move operator. That is, okay, you understood, right? So key insights, different neighborhood definitions. Okay, this is very important. Different neighborhood generations create different edges. So what I have done here is from S1, suppose this red line is inversion operator, right? We have talked about inversion operator. From green line, I will say swap operator. Pencil is not working properly. Okay, so suppose from this you can go here to swap. You can go here via swap. You can come here via swap, and you can come here via swap. So you see, the edges is defined using the neighborhood operators. A solution can be a neighborhood. So suppose this solution is a neighborhood of S1. So S4 is a neighborhood of S1 using swap operator, but it is not a neighborhood of S1 using inversion operator. Solution S5 is a neighbor of, not neighborhood, neighbor. S5 is a neighbor of S1 using both inversion and swap operator. S3 is a neighbor of S1 using inversion operator, but not swap operator. So this is important because when we go to landscape analysis, this becomes important. Is it clear? Different neighborhoods leads to different edges, different set of search spaces. That will define your local optima, connectivity, and search difficulty. We will talk about this because this is very, very important idea in metaheuristics. Is it clear? Is it clear? Okay, now you just think. Suppose this has an objective function of 50. This has an objective function of 52. This has an objective function of 60. This has an objective function of 51. And this has an objective function of 65. And this is 70. This is 80. And suppose this is 100. Now you see, when we are talking about inversion operator, S1 is a neighbor of, so suppose this is not 51, this is 54. So in that case, S1 becomes local optima using neighbor inversion operator. You see, S1's neighbor has 80, 70, 65, 60, and 54 using inversion operator. Please be clear. Using inversion operator, S1's neighbor are 54, 80, 70, 65, and 60. Therefore, using inversion operator, S1 is the local optima. But if you use swap operator, you see S1 is not the local optima. You can go to S4, which has a lower objective function, that is 50. Therefore, your neighborhood operators defined the structure of your objective function space, objective space. You can have multiple local optima. Yes, yes, considering minimization problem. Yeah, I am always considering minimization problem. Considering minimization problem. So the neighborhood operators defined the structure of your objective space. If your neighborhood operators are such that the solutions with lower objective function value are clustered together, then you have a very good structure. Your structure is such that all the local optimas are coming together and you have a big shallow depth in the objective value. But if you have some neighborhood operators that create local optimas in different places, then it is very difficult to move from one point to the other. So the idea is just that your move operators define the structure of your objective space. Is it clear? Because this is very important idea. This is a very important idea. This is known as fitness landscape analysis. The value of your objective function is defined. So the space which is obtained is actually governed by the operators you are using. Is it clear? It is very important, by the way. Is it clear? Right. I hope it is clear. Okay, so that is what fitness landscape analysis means. The landscape means the objective function. What are we doing is we have a geographical metaphor. Each solution is a place in the ground, and the objective function determines its altitude. So suppose you have a place in the ground, and the objective function is its altitude, like this. Okay, so this is the landscape, and landscape analysis is very important. If you don't use appropriate move operators, so you will get a landscape like this. But suppose you generated a move operator such that all these local optima come together, then what will happen is you will have a local optima like this. So your move operator defines how your landscape will look. Is it clear? Any questions? Any questions? Okay. Um, um, is it clear? Are you able to understand this? Or am I going very fast? Okay. All right. So I'll just take some time and I'll complete this. Okay. So yeah, so your landscape can have multiple features. It can have local optima like this, multiple local optimas. You can create neighborhoods in such a way that you have a global optima. You can create plateau regions as well. Like this you can have. Yes, reference book, I'll tell you. I'll just tell you. Just let me finish. I'll take 2 minutes and finish and then I'll tell you. So this is how the landscape will look like. And it will change depending upon the representation and the move operators you are using. Okay. I will stop right now because this idea takes different to us in different discussions. So this is where we stand. A quick comment on distances. So this I'll tell you. Just give me. So your neighborhood distances are defined in terms of number of move operators you apply. So suppose from S1 to S5, you came via one move operator, one swap operator. So that it is at a distance of one. So suppose from S5 to S4, you can go. So you see from S1 to S5, you can go via one swap move. And from S5 to S4, you can go another via one more swap move. So the distance of, and this is not there. Suppose this is not there. So the distance of, so the distance of S1 to S4 is two swap moves. One from S1 to S5 and then from S5 to S4. So two swap move is required from going from S1 to S4. This is known as the distance. So this way you can define distances in this metaheuristic concept. Okay. For continuous, you can just take the Euclidean distance, and for discrete, this is how you take. So for binary, you can just say how many bits you are flipping. If you are flipping one bit to obtain the neighborhood, it is just distance of one. If you require to flip 2 bits to move to another solution, so those two solutions are 2 bit flips apart. So the distance is 2 and so on and so forth. Okay. This is it. This is it. So we have completed the landscape analysis. What remains is the initial solution. What should be the initial solution? And then local search. So I'll quickly take your comments and I'll just show you where we are and what we need to do. So you see, we have completed till this part. We have completed search space, objective space, exact method, approximate method, heuristic versus meta-heuristic, greedy algorithm, solution representation, neighborhood, fitness, landscape analysis. We just have initial solution to talk about how to generate initial solution, then local search, then we'll move on to simulated annealing Tabu search for tomorrow. So this is the idea. And if you want PPTs and other resources, this is the link. I have this website. You can go to this link. You can, there's a page I have created for this course specifically. It says the title of this workshop, an introduction to metaheuristics. All the PPTs will be available there, and the recordings, just a minute, and the recordings will be available once I receive the recording from IIM Ahmedabad. And this is the book. This is the book I am referring to. I have this book over here. This is a very good book. You can use it. And I will take other comments. If you have any personal discussion to do, we can do it later, or you can just email me. Today's PPT will be uploaded in the website, which I am showing over here. You can take a screenshot just right now. Okay. Multi-objective optimization problem. There is a book by Professor Kalyanmoy Dev. It is published in 2001, I guess. Yeah, it is a very good book on multi-objective optimization. Please, can you tell me the book? This is the book I have written over here, reference book. From Metaheuristics, from design to implementation, from E.G. Talbi. It is there in here in front of you. Okay, what I showed. This is the book I showed. The book which is written here, that is the same book which I am showing right now. Is it clear? Okay. All right. So I know I was a bit fast, but I have to cover few things. We can discuss tomorrow. We will let go of one algorithm and we can discuss tomorrow. If you have doubt, you can email me, and please visit the website for more details. All right. Thank you. So I'll leave. Um, Yeah.